Now we have already generated the sine function using the CORDIC algorithm. Now we're going to go on and see how we generate the cosine. Now this is going to be relatively straightforward, as we've done most of the work generating the sine function. So first of all, let's have a look and see the assembler. So again, if you head into Visual Studio Code Editor and we're in RTM16, and we can head into the tool section, and you can see we've got assembler.py. So we've got this opened, and again if we head down to this line here, and you can see we've got the next instruction, which is going to be our CORDIC cos. So it's going to be called CCOS. It's the next instruction along, so the 0 here goes to a 1, and it's the same setup. We're going to have 3 different addressing modes. One will be a number to a register. So that addressing mode was what we seen whenever we generated the sine function. We had a number, and the value was then held in a particular register. We also get the register to register, so it means that the number that we're looking for already exists within a register. Okay, so register R0 would contain, say, the angle 45 degrees, and it would return it to register R1, which would be the sine of 45. And we also could have an address to register, so the angle 45 degrees could be held within a register, within an address location within the RAM, and we will return the sine or the cosine of that angle to a register. So those are the 3 addressing modes. Now that's all we really need to do as far as updating the assembler. Now let's have a look at the actual instructions and all of the micro instructions that make up that instruction. So if we head into our run task, edit microcode, and this will run up our command line interpreter. And that's it run up. So we can then type in micro steps, and it's going to be the CCOS, which is going to be our instructions. That's CORDIC Cosine, and the addressing mode will be 0. And you can see here we've got our micro instructions. Now the micro instructions are going to be really very similar to the micro instructions for our CORDIC sine for this addressing mode. So the instruction address register is enabled and the memory address register is set. But this time here we've got the value 9, so this is going to be 1 and 8. So 1 plus 8 is 9. So the value of 9 is the reset value for our CORDIC unit. So this resets the CORDIC unit. We put our value that we get out of our next address location, which is going to contain, let's say for example, the angle 45 degrees, and we put it into the cache register, and then we enable that cache onto the bus. Now the only difference here really is that instead of choosing the number 7, which was the number for the sine function within the CORDIC unit, we're going to use the number 8. So ALU 3, so that's 1, 2, 4, 8. So this is number 8. And this generates the cosine function. Now we could in fact have just used the number 7 and it would still generate the cosine function, because whether we use 7 or 8, we're going to generate the sine function and the cosine function. The only one that we really would need to change is the very last one down here. So we have to ensure that this says ALU3, because we're going to be using this in order to output the final value, which is the cosine value from the CORDIC unit. And we're going to save it in the accumulator, and then we're going to take it from the accumulator and put it into Reg B, say for example register number 3, and then we're going to do the housekeeping again. So we're going to add 1 on to the instruction address register, and then save this in the accumulator, and then again save it into the instruction address register, so that we're now pointing to the correct location for the very next command. And then there's the stop function. So this is all very similar to the sine function we've seen earlier. Now let's head into our CPU, and we'll just have a quick look at the position where we get our cosine function. So if we head into the floating point unit, we've got the CORDIC unit here, and you can see here that we pick off the cosine from this point here. So irrespective of whether we're using 7 or 8 here, it will run through this rotation mode for our CORDIC, and it will give us both the sine and the cosine functions. The only reason we really need to put in the value for our A is whenever we have the very final value come out. And when that final value comes out, we're going to have to ensure that we pick off the cosine function to pass to the output. So we have to make sure that in the final iteration for the CORDIC that we choose this cos instead of the sine, and the cosine will get fed through here. So this select button will be at a value of 8, and the CORDIC cosine will get passed through instead of the CORDIC sine. So finally, let's look at the actual instruction. So we can go into our .asm folder, and we can create a new file, and we'll call it ccos_test.asm. Again, we can put in our .code, and it's 0x8000, and then we can put in our actual command. So the commands, well, I will actually show you the 3 commands that we will have for our cosine. So these are our 3 different addressing modes. So we could have, for example, ccos, and it's just a number, so we would have hash 0.78395. okay, so this is a number which represents the radians. So this is the angle that we're trying to find the cosine of, and we're going to put the result in register R0. So that's the addressing mode 0. Now the other addressing mode would be ccos R0, R1. In this instance here, we would find this number here in register R0. So this number would have to be placed within register R0 for this to work. And then whenever we get the output, it will place the output in register R1. Now the other option would be ccos, and it would be the number, let's say for example 0x8500, R3. So this would be the third addressing mode. So we would be looking to find the angle in radians within this memory location. So the angle in radians here would be in this memory location. So we would go to that memory location, we would pull out this angle in radians, we would go through the C cosine, so the CORDIC cosine, and we would put the answer in register R3. So these are the 3 addressing modes, and those are the same 3 addressing modes that we've got available to us for the sine functions and for all of the rest of the CORDIC functions. Now we're going to have the same problem that we ran into with the sine function. The sine function was only going to be accurate from minus 90 degrees to plus 90 degrees. So we had to find a way of increasing the accuracy over a much wider input. So we did that with the folding function. Now we can do the same sort of thing with the cosine function. And in fact, whenever we do this, you'll see that in the end we don't even need to use the cosine command. We can still just use the sine command in order to generate the cosine command. So let's have a look at this now. If we head into the fixed point, the floating point library, so this is the floating point library here, we will head all the way up to the top. Now we're going to look for the floating point c cos, okay? So we've got float underscore c cos, so that's the CORDIC cosine, and it exists at 5440. So we put the 0 cross 5440 in here, and we'll look and see if we can find it. Okay, so this is it down here. So we've got a subroutine here that's going to be called our CORDIC cos, okay? So exactly how are we going to use this? Well, in order for us to generate the cosine, we can do this quite simply by taking the value x away from pi by 2. So whenever we take the value x away from our pi by 2, we change the function from the value for our sine into our cosine, because the sine and cosine are directly related and they're just out of phase by pi by 2. So we go through this process here and we subtract, in this case, subtract R1, R0. So R0 is equal to pi by 2, which is this number here, minus our input x. And then we then take this and we pass it into our folding function. So this folding function will then put the value into the range 0 to pi by 2. And now we don't need to use the cosine instruction, we just use the sine instruction. So we use the c sine R0, R0, okay, and the result will come out in the register R0. Now you'll notice here we've got some housekeeping. We've got the push R1 and pop R1 because register R1 is going to be changed within this subroutine. So anything that's going to be changed within the subroutine, we're going to have to take the original copy of it and place it on the stack. And then when we're finished with the subroutine, we will return the value back off of the stack into that register. It's almost like we've never been there, okay? So we return everything back to exactly the way it was previously. So this is a nice and neat way for us to generate our cosine function. So we don't even really need the cosine output, we just need to use the sine output. So what we could do is, instead of using the c cos, we could jump to subroutine and we could do float underscore c cos, and then the end. Of course, we would also have to add in here exactly where the float underscore c cos is. So we'd have to have EQU float underscore c cos and the memory location. So the memory location for it is here, 0 cross 5440, 5440. Okay, now as long as we ensure that register R0 has the value in radians of the angle, which is our input, then it will return the answer back into R0. So this is a preferred method because with this method we've got a way to generate the cosine of a function using the CORDIC unit for an entire range, the entire domain of inputs. So it won't just work between minus 90 degrees to plus 90 degrees, it will work over the entire range. So let's finish this off. Let's say we put in data hash 0.785398, which is 45 degrees in radians, and we're going to put this into register R0. And we'll take these, because we're not going to be using them, out of the way. We'll take this as well and we'll put it at the top just to make it a little bit tidier. So this is the final code here. So we have the 45 degrees in register R0. We jump to subroutine float underscore ccos. It goes there and it works out what the cosine is for this angle using the CORDIC unit, and it returns the value into register R0. So we can go terminal, run task, assemble file, and that's assembly successful. So let's go and we'll load this up. So we'll drop into the RAM, edit contents, and we're going to open up the file within the machine code folder, and it's called CCOS. So CCOS underscore test.mc, and this is the code here. Close the window and we'll run through this. It'll take a few seconds because we're going to have to run through a couple of different subroutines, and it will run faster than this. It's just running a bit slower because I'm recording this at the same time. So there's the final answer, which is our 39888, which is going to be approximately 1 upon our root 2. So if we put our final result in, 0 cross 3988, and you can see that is 0.707. So this is very close to 1 upon root 2. So in the next video, we'll look at how we can generate the tangent function. And really, in order to generate the tangent function, what we can do is we can generate the sine function and the cosine, and then we can divide them, and that'll give us our tangent function. So that's all for this video. Thank you for listening. I'll get you on the next video. Goodbye.